In this video, we will be considering different types of experimental uncertainty and the ways in which they can be combined to get an overall measurement uncertainty. In this analysis, we will roll 10 dice, and each die has a 6 on one face, and if they were perfect dice, the probability that any one die would roll a 6 would be given by a probability of 1 divided by 6, or a probability of 0.167. However, we will not be using perfect dice, we will be using homemade do-it-yourself dice, which, due to uncertainties in their fabrication, we can estimate there will be an uncertainty of possibly 20% in the probability for each dice to roll a 6. So to calculate the probability that a particular dice will roll a 6, we will assume a probability which is randomly selected from a normal distribution of probabilities with a random probability where the mean value of the possible probability is 1/6, but the standard deviation variation in those probabilities is 20% of 1/6. So that would be 1/6 multiplied by the uncertainty which we have in B14, which is currently at 20%, divided by 100. Enter. So we can see that we have a randomly selected probability for the first dice of 0.125. This is based on a mean value of probability of 1/6, but with a percentage standard deviation given by the value in B14. If we press F9, Excel will give a new random value and give a new random selection for this probability. So we press F9, and so we see we have a new probability. Press F9 again, and a new probability. So we'll apply this formula to all of the dice by dragging this formula down, but before we do that, we will put a $sign in front of row 14 in this formula so that that does not change when we copy the formula. So now we have random probabilities for each of the dice. The next step is to consider the number of 6s that will be observed if we roll the dice 200 times, given the probability P that each roll will result in a 6. And for this value we must use the binomial distribution. So we enter the formula equals binomial, and we'll use the inverse, and out of trials we will have 200 trials, and the probability for each trial giving a 6 is given by the value in B3, and we wish to select this possible value randomly from the binomial distribution. So we will have the random value for the probability, and we enter. So in this calculation, for dice 1, for a randomly selected probability of 0.134, we could see 34 6s. And if we copy this down for all the dice, this would give a number of 6s based on the probability of a 6 from each dice. So we have now set up our experimental model with randomly generated probabilities of throwing a 6 for each of 10 dice, and then in each case a randomly selected number of 6s based on the binomial distribution using the particular probability from each die. This model includes both the uncertainties due to the different dice, so this is a subject uncertainty, but it also includes the binomial uncertainty in the numbers of 6s thrown for a particular probability. And we will investigate two methods, method 1 and method 2 of analysing the data. Method 1 just adds up the total number of 6s observed for a total of 2,000 rolls of dice. So we just add up the number of 6s and then calculates the mean proportion by dividing that sum by 2,000. So that equals C17 divided by the total number of rolls, 2,000, gives a mean proportion of 0.1520 for this random selection. And if we wanted to calculate the uncertainty in that value, the only information we have is that this is a randomly generated proportion, and we would have to use the standard formula for the uncertainty in a proportion, which would be equals 1.96, then multiplied by the square root of the measured proportion multiplied by 1 minus that proportion divided by the total number of observations, which would be 2,000 in this case, giving an uncertainty of 0.0161. The alternative method of analysing this data is not to average all of the values immediately, but to calculate each proportion separately for each die, which would mean taking the frequency for each die and dividing by the 200 rolls for that particular die to get an individual proportion, and then to copy that formula to calculate the proportions for each of the 10 die. To calculate the average or mean value, we would take the average of these proportions, which would be equal average of that range, so would be 0.1585. And actually we can see here that calculating the mean proportion using method 2 has given us the same value as the mean proportion for method 1. The reason that these are the same is that each die has been rolled the same number of times. So each die has the same weighting in terms of information when taking an average. To calculate the confidence deviation for method 2, we have got 10 results. So we can take the sample standard deviation of those 10 results. To calculate the standard uncertainty, we would have to take the standard deviation from E15 and then divide by the square root of the number of values, and we have 10 values. And to calculate the confidence deviation, we would need a t-value, and we would take the two-tailed t-value, which would require the probability, which for a 95% confidence interval is a probability of 0.05, and degrees of freedom would be the number of measurements, 10 minus 1. So the confidence deviation for method 2 would then be the product of the t-value multiplied by the standard uncertainty, giving a result of 0.0248. Overall, we find that the two methods of calculating the average proportion gives the same mean value because we have equal weighting between all of the measurements, but the confidence deviation for method 1 is considerably smaller than the confidence deviation for method 2. This is because method 1 has ignored the subject variation due to the different dice. By taking just the overall sum without investigating the variation within the sum, there is no information about how there may be differences between the different dice. So this underestimates the real uncertainty in the result. Whereas method 2 includes both the subject uncertainty and the probability uncertainty in calculating its overall result and gives a more realistic confidence deviation for the result.